Okay, back to perspective. So, what were we doing? We were trying to do system analysis. Remember something about that? We're trying to figure out what comes out of a system given the differential equation and an input and some initial conditions. And we've already seen we can do that we can get numeric values by using a table method, using recursion, just basically running the difference equation. And last time we embarked on how we could do it analytically, how we can find an analytical expression for the output using an analytical expression for the input and the difference equation. And that was by solving the difference equation using zero state responses and zero input responses. This was the example problem we did. We took that particular recursive difference equation, applied a two-size unit step to it, had some initial conditions, and when we did that, we found the zero input response looked like that. The single input case zero state response had that form, where the one term in green was the part that we called the forced response, and the other part was part of the natural response. But that was for not that difference equation, but for a junior version, a single input case difference equation, where we dropped off the x terms with delays. So that was for the difference equation y of n plus 1/2 y of n minus 1 equals x of n. So we dropped off that x of n minus 1 term for the single input case. Then using linearity and superposition, we were able to take that single input case zero state response and make it the response for the general case, the one that did include that plus 1/2 or plus x of n minus 1. And that gave us the following expression, which included a time-delayed version. And then to get the total response of the system, we added the general zero-state response to the zero input response and got the total response. So that's in brief what we did, and last time we went through the mechanics. And so were there any questions on how we did that, on the steps that we took to do that solution, because we're going to need to be able to do that. So all was kind of clear, the whys, wherefores, and hows. All right. That's, in fact, if we plotted the input step, the 2u of t is the blue samples, and then the green samples were what would have come out if we just put different values of n into that equation and ran it through recursion. Those would be the sample values we would get out of that. So you see you've got some overshoot, got a little bit of ringing, but it does kind of settle down to a constant value. All right. Well, for this method, there are two special cases that we have to handle, just like there were two special cases for solving differential equations, and it's the same special cases as it turns out. That's if your input, your forcing function x of n, has a same shape as one of the natural response terms. And so, for example, if you had a natural response term with a 1/4 to the n in it, and you happen to also drive it with another signal that was 1/4 to the n, then our form of a natural response matches up the form of the forced response. And then we have to deal with that with a slight change to our process so that we don't have those effects overlapping each other. And the other special case is if your characteristic equation has multiple repeated roots, the same roots of that characteristic equation. For example, this equation, if we took the characteristic equation that turned out to be z squared plus z plus 1/4, that's z plus 1/2 squared, and that would we have a repeated root at z equals minus 1/2. In that case, the form of the natural response would change. So how do we handle these? Well, for the case where the forcing function matches the form of the natural response, we go back to our forced response table, where we look at, on the left, what the shape is of my input signal, and pull off from the right what's the shape of the forced response. We then have to go look at the asterisk, the fine print. So a couple of these have asterisks by them, and the fine print is that if you do have ones that have these generally exponential forcing function kind of terms, our natural responses will tend to be exponential functions. And so if you happen to do that, you hit them with the same exponential function, then we've got to change the force response. It's still the same form shown, but I may have to multiply it by an n, or some power of n, where the and the way we tell is whether that alpha, that exponential function, is a root of the characteristic equation. If it happens to be a repeated root, which is our other special case, then our force response will get multiplied by n raised to the power of the highest number of times that root repeats. Now, usually we're not dealing with a repeated root case. We're not dealing with both special cases at once, so usually it's just n to the first power. But there could be cases where you have both overlapping. Let's skip that. So let's do an example on that one. If we took the same problem that we had before, and let's make sure we've got it referenced there. Let's go back a couple of slides to see it. That same problem. All right, so our differential equation was y of n equals x of n plus x of n minus 1 minus 1/2 y of n minus 1. But now instead of putting a unit step in, we put in a different one, maybe a minus 1/2 the n u of n. Would the zero input response change? No, because that's a response to the initial conditions. We didn't change anything with that. We're just changing the input. So the zero state response is going to change. All right. In this case now, if we're looking for the zero state response, again for the single input case, we're going to need a forced response. And normally we would go in the table and say, oh, okay, well, I've got a 1/2 to the n u of n. Let's go to the table. And in that second row there, so normally we would just come in and say, well, fine, the force response is, well, some unknown c times our minus 1/2 to the n u of n. But we also know from our previous solution that the natural response has the form k times minus 1/2 to the n, which matches up. And that comes from the fact that our characteristic equation had roots equals minus 1/2. So the roots of the characteristic equation gave us a natural response that had this form. It's the same form that my force response wants to be. And so because of that, I'm going to need to add, it's not just c, but c times n. And then, it's not t, it's n's. And I'm going to need the force response at n minus 1 to plug it back in the equation. So that's going to be a c times n minus 1 times minus 1/2 the n minus 1. And we would find it, solve for that unknown c using the single input case difference equation, and plug in the force response into it. which says that the y force response of n plus, make sure I got signs right, 1/2 y force response of n minus 1 should be equal to x of n. And again, I don't include the x of n minus 1 term because it's my single input case. Our force response we have there, c times n times minus 1/2 to the n. And we'll leave off the u of n's for the moment. Plus 1/2. Our delayed force response is a c n minus 1 times minus 1/2 to the n minus 1 equals the actual input, which was minus 1/2 the n. Okay. Now, where do we go from here? First thing we're going to do is go higher, so you can see it. No, that first term's okay. C times n minus 1/2 to the n. That I'm happy with. Not liking this 1/2 to the n minus 1. Let's see, c times n minus 1, don't lose that, times minus 1/2 to the n. See, what I'm trying to do is get everything looking like a minus 1/2 to the n so that I can equate the coefficients. But this n minus 1 is troubling. But I think I can express that like that. And still equals minus 1/2 again. And what is this here? It's minus 2. So I've got a bunch of, I've got Cn, I've got 1/2 c to the n, I've got minus half c, distributing that through. Oops, gotta be careful here. Let's not do that yet. Let's take care of this. So I've got a minus 2 times that 1/2. So that's just going to give me a minus to the n minus 1. Now we can equate terms. So Cn minus Cn, both times minus 1/2 to the n, they're going to go away. My minus minus is going to give me a plus. C times minus 1/2 to the n equals minus 1/2 to the n. I hope. So therefore, C must be equal to 1. So my force response of n is just 1 times the original assumption minus 1/2. No, not the original assumption. 1 times n, and that's the n, and if you like, times n greater than 0. And then the rest would proceed from there exactly the same way. I would find a natural response piece to finish off the zero state response. I'd generalize it, do the general case, combine them together, get all the goodies. But so the main thing that changed was now I've got this n in there. Let me just set up the question. Between here and here. So let me not be quite so quick. So if I rewrite that and keep me honest here, minus Cn times minus 1/2 to the n minus minus plus 1 times C minus 1/2 to the n. Just multiplying out all these terms here. Did I get that right? So that's the step between here, and then these will cancel. So just to set up the rest of it, but no sense in running it all through. The single input case zero state response then would be the forced response plus another natural response piece different from the zero input response. So we would use this known one, n times minus 1/2 to the n, and some unknown coefficient with the natural response form. And solve for K2. Using the initial conditions, y of minus 1 equals 0. Okay. So again, the only thing that changes was the form of the natural response, because it's the same as the form of the changes the form of the forced response, because it matches up, the table value matches up with the natural response. I had to add this n, and that just affected through here the net forced response that we got. When all is said and done, notice that what I'll end up with is two distinct terms in my zero state response. I'll still have a natural response that looks like this, a forced response that looks like this, but they're different. They're made different by this n. They won't cancel each other out, or they have their own unique place. Question?
I'm just curious, are all these operations, are those supposed to be square brackets?
Oh yeah, they're all supposed to be square. I'm getting lazy. Yeah, everything's discrete time. Yeah. How did the n end up in there? So that was my starting assumption of the form of the forced response. The table said it's just this, but when I have this special case that it's laying on top of one of the natural response forms, then I have to add not just C, but I have to have an n out in front. Because the root of the characteristic equation gave me a natural response that has the same exponential form as the forced response, the forcing function. So that is the definition of our first special case. Yeah. Single input case. Yes. So it's the second, it's the alpha to the n row. No, normally it would be C, alpha is 1/2, so alpha would be -1/2 in this case. So normally that would be it, but asterisk, fine print, we're doing this. We need to multiply that force response by n raised to the p, where p is the number of times that root shows up, that characteristic equation term shows up in the natural response. Yeah, if this had 2 roots, then the natural response would have 2 terms, and this is jumping ahead to our next thing. It would have an n times -1/2 the n term, and then the force response would have to be an n squared. So the force response is always going to be 1 power of n ahead of the natural response pieces. Okay, and so yes, exactly that is our next special case. First, other questions about this one? Okay, if you're the other table that we use to change the roots of the characteristic equation into natural response terms, we do have special rows to handle these cases where you have repeated roots. If you have a singular root with an exponential, it's a k r to the n term. But if it's repeated p plus 1 times, then, or it appears p plus 1 times, then we have to not just some k out in front, but we have some power of n in front. So the power of n is up to the level that's 1 less than the number of times the root appears. Oh. So like we said, if the root appears twice, I'll have 2 terms, the original one plus an n to the first. If this root appeared 3 times, then I'd have another term, n squared times -1/2 to the n. And if you did this and you hit it with a forcing function that was the same, this would move up to n cubed. Yeah.
What do you do in a case where you get, like, say, c equals plus or minus 1/2? Different roots for your characters. What do you do that?
We treat them separately. They're considered distinct roots then. Yeah. So I would get a 1/2 to the n term and a -1/2 to the n term. Yep. Okay. Question.
If your force response is the same root as one of them, is it still c n? Like, I see what you're saying is you had plus and minus 1/2.
Well, again, so
One of them for one root is -1/2, then the n still has to be the second power.
so if the forced response does match up with one of the terms of the natural response, it's going to have a power of n that's always 1 higher than the highest power in the natural response. So if the root only appears once, we get an n to the first. If the root also appears twice in the natural response, we'll get an n term into the first in the natural response and an n squared over here. And like this equation, if we have 3, then we'll get n to the 0, n to the 1, n squared in the natural response, and then n cubed in the forced response. Okay. So by the way, so that problem, that special case we solved, that's how that output and inputs would look like on that one, where again blue is the input signal. It's a 1/2 or -1/2 to the n, so its sign is changing every other one, so it's oscillating. And the green one's also oscillating, kind of lagging behind it, but they both do settle down eventually. Okay. So just to take a case, one of those special cases for that last one. You talk through the mechanics of the whole thing, but let's look at this one. This is an example your book gives for the special case of repeated roots, and it unfortunately follows a slightly different way of thinking. So let me do it for us in the context that we're used to. So that's this problem here. It's the difference equation shown, y of n plus, minus y of n minus 1 plus 1/4 y of n minus 2 equals x of n. We want to solve this for input x of n is a unit step, and all the initial conditions happen to be 0. What order system is this? Heard it. Second order. The highest order delay on the y side is 2, so it's a second order system. We're going to need 2 initial conditions, and so we're given y of minus 1 is the same as y of minus 2 equals 0. That means I have a special kind of system. This happens to be a relaxed system. There's nothing left over from before. So my stand over here is just like that. It's nice and quiet. It's stable. I'm going to sneak up on it and give it a unit step. See how it responds. But it was relaxed to start with. Okay. All right. What is the characteristic equation of this system? Z squared minus z plus 1/4. Would everybody agree with that? Equals 0. You might have started with 1 minus z to the minus 1 plus 1/4 z to the minus 2 equals 0. Multiply everything by z squared and get the characteristic equation. So the roots of that, that's, what is that? That's minus a half squared. Yep. So we have 2 roots. Z is a half and a half. So anything that's a natural response is going to have the form k times 1/2 to the n. Well, actually I need 2 terms, right? I need a k1 times 1/2 to the n, and I'm going to need another one, and it's not just k2 1/2 to the n, but this one will get an n out in front. And that's how we're handling this special case where we have repeated roots. Relaxed stating. So how about, what's the 0 input response of this system? It is a natural response. Well, it's part of the natural response. Except, do I need to solve for it? What's that? I plug in my initial conditions. What are my initial conditions? 0. If all of my initial conditions are 0, what's the 0 input response? System was relaxed. There are no initial conditions, so there's no response to the initial conditions. So the 0 input response has to be 0 in this case. So everything, it's total response now is just going to be a zero state response. All right, we start with the single input case. Do I need to change anything to make this a single input case difference equation, sorry. Of course I have it. What should I change? Say it, you know it. You're right. What's that? Force response. How should I change this difference equation to transform it into a single input case difference equation? Leave it alone. It's already a single input case difference equation. Don't mess with it. Okay. Yes, the only x term I have is an x sub n. It already is a single input case. So when I find the zero state response, I will have the general zero state response. And by the way, because there is no zero input response, when I find the zero state response for the single input case, I have actually the total solution, because everything else is zero. Okay. So of n, we need a forced response piece, and we need a natural response piece. Okay. What's the forced response look like? Forcing function. X of n for n greater than or equal to 0 looks like what functional form? Constant. Equals 1. Constant. So my forced response is also going to be a constant, particularly since this x of n, where is he? Where is he? He doesn't look like these guys. It's not a 1/2 to the n, so I don't have that special case for the forcing function. Okay. So then we should be able to plug this back in the original difference equation, which looks like yn minus 1 plus a quarter. The forced response of n minus 2 has to be x of n. And that's a constant. That's a constant. Plus 1/4 times a constant equals a constant 1. So 1 times each step. So 1/4 c is 1. C better be 4. So my zero state response for the single input case and for all cases is going to be the forced response plus a natural response piece. And I know the forced response is 4. The natural response has that form, what was it? 1 times 1/2 to the n plus k2 times n. 1/2 to the n. And then the rest just progresses the way we normally would. We use the single input case initial conditions, which actually also happen to be the general ones too. Y of minus 1 is 0. And we plug in n equals minus 1 in this equation. We get 4 plus k1 times 1/2 to the first power plus k2 times, minus 1. Minus 1 times 1/2 to the minus 1 equals 0, which is another way of saying 4 plus 2k1 minus 2k2 equals 0. And the second initial condition, y minus 2 equals 0. Plug in that here. 4 plus k1 times 1/2 to the minus 2 plus k2 times minus 2 times 1/2 to the minus 2. Which gives me 4 plus 4k1. That's a minus 2. So that gives me a 4 up there times minus 2. Let's just make sure. Yep, that's minus 8k2. So I've got two equations, two unknowns. I'd probably multiply this by 2, subtract them. When you do, you find that k2 is minus 1 and k1 is minus 3. So my zero state response, which is my total response, my single input case zero state response, which is the same as my general zero state response, which in this case is the same as the total response. These are the same because my equation was a single input case equation. These are the same because there is no zero input response. So it's just my forced response, which was a 4. Now we'll drop in our u of n's. And k1 minus 3 times the 1/2 to the n. And k2 is minus 1. 1 times n times 1/2 to the n. And I should sprinkle liberally with u of n's because these are all for n greater than 0. So let's knock it out of the way. Questions? So on these special cases, it's all in the setup, right? We carried it through just to get a little more practice on the method, but nothing else really changed except form of the forced response or the form of the natural response that we assumed to start with, and then the rest just carries out through the same methods as before. Questions? A lot to digest. Need some practice. Yep. In the which, where, who? In here? Sure. I could do that. I could indeed. Other questions? Okay. Again, this parallels exactly the way the same method of undetermined coefficients that we use for solving differential equations. Very similar. Just now we don't have to take derivatives, we do delays instead, which is kind of nice. Please do make sure you're comfortable with how to do all those, how to take single input ones, generalize them, how to break things up, zero input, zero state. And when all is said and done, I can recognize, here's the forced response piece. How do I recognize that? Well, it has the same functional form as my input signal. That means everything else must be the natural response pieces. Only you got to be careful of if you are generalizing a zero state response. The force response may have this kind of shape plus some delayed versions of it as well from the generalizing process. Okay. But if you understood those three examples, then you've got solving difference equations under your belt. Ooh, 5 minutes. Can we make some more headroom? First questions are okay. If anything up there that didn't make sense, we're all good. I just wish we didn't have to do this stuff. I'm really looking forward to the fact that someday, not too distant future, we will be able to do this with Z transforms, and it'll be a whole lot easier because it'll be just plain algebra. Okay. All right. One more way to do system analysis, and you knew this was coming. You were just waiting with bated breath. You've been hoping we would get there, and yes, indeed, finally the day has arrived. Well, at least the lead up to the day has arrived, and that is that we can use recursion, we can solve the difference equation, or we can do convolution to find the output of a relaxed system for any input on any linear time invariant system. And if we're going to do convolution, we need convolution with an impulse response, just like we did in continuous time systems. Except the impulse response for discrete time system is actually a rather unusual little fellow. It's not really an impulse response, but it's the unit sample response that we're after. H of n, just like we had H of t was the impulse response in continuous time systems, we use little h of n as our impulse response of sorts for the difference equations for discrete time systems. And what is that? What is h of n? Well, if we have some linear time invariant system, now we have our inputs x of n, output is y of n. H of n is what I get if my input is a unit sample sequence. Unit sample sequence. All right, that was that thing. Versus n, it's zeros everywhere. Up zeros everywhere, up to n equals 0, and then it jumps up to 1, and then it jumps back to 0. So that's just crossing there, it's there. A single 1 at n equals 0. And then what comes out is what we call the unit sample response. Let me give that a name, h of n. So literally the response of the system to a unit sample is a unit sample response. Why does it matter? Well, if I know the response of the system to this simple input, I can predict the response to any input, because any input can be expressed as a bunch of scaled up or delayed versions of this. And so actually that statement written in summation form is this one, which turns out to be the convolution summation for discrete time systems. It makes even more sense than it did in continuous time systems, because I don't have to worry about integrals and weird impulses, but this even makes sense. And we'll go through that. So the unit sample response is going to be another way that I can describe for you the complete information you need to find the output to do system analysis. It's another system description. The difference equation, has all the dynamic information about the system. And so does the unit sample response. It's all in there. Everything I need to know is contained in that. So it's another way to describe the system. And we're going to use linearity and time invariance, those assumptions that we made about our systems, because they are LTI systems, to use the unit sample response to predict the response to any other input. And this is the first of a number of techniques that work the same way, that say if you give me some complicated input sequence, who knows what shape it's got, I'm going to represent that or its transform with some simpler function, whose response I know, then I can give you the response of the complicated system as just a linear sum of simple responses. And that's what we rely on superposition. That's why we can only do it with linear time invariant systems. So we'll give you the setup. If you have a relaxed, general differential equation, linear time invariant system with that kind of difference equation, we can find the unit sample response values just like we've done so far. We can use recursion if you want numeric values, or we can solve the difference equation for this particular input and set up a relaxed set of initial conditions and see what comes out. But just like what happened in continuous time systems, I can't solve necessarily the system for a unit sample at n equals 0 and nothing else, because it messes up my force response and approach. So we're going to need an alternate model for the unit sample function to do it. And you're just going to have to wait till Friday to find that out. So, see you then.